Welcome to Spring LIB.
To start with, I'm just going to draw what our products are here, or what the species we're interested in are. And it looks like, to me, just based on the empirical formulas, that we've got phenol as one of our acids, and the other acid as glycerol. Oops. Yeah. Okay. And so what we're doing is an equilibrium. We have phenol with the O minus, right? So it's been deprotonated. The conjugate base of phenol, phenolate, plus our glycerol. In equilibrium with phenol and the deprotonated glycerol. Okay, so this is the reaction we're interested in. And I'm just going to try to answer your question because I can't see what K, the equilibrium constant, is. But based on the fact that the answer is C, which is the weakest acid in this equation, they're saying that this is the weakest acid in this equation, right? So I'm going to try to relate that fact to K and what that tells me, right? So if this is the weakest acid, that means that this is the strongest base. Oh, sorry, I made a mistake here. Sorry. I'll step back and then I'll explain that. So hopefully that's not too confusing. Right, so the transformation we're showing is the transfer of this proton from glycerol to here. So maybe let me draw that in red. We can see that, right? This proton gets transferred here. Yeah. Great. And you can kind of think of it as this negative charge getting swapped as well. So we'll draw that in blue. Okay, so that's what this K is in relation to. If the K is big, this is the favorable side, the product. If the K is small, then this is the favorable side. So that's important to remember, what the meaning of K is, right? Okay, so they're saying that this is the weakest acid, right? The phenol is a weak acid. Recall what that means. If something's a weak acid, it means it's less likely to give up its proton. Another way of saying that is that its conjugate base is a strong base. So let's say strong base, weak acid. Okay. So this is telling us that the right-hand side is more favorable, right? Why is that? Well, a strong base is going to be more likely to steal a proton, right? And a weak acid is going to be less likely to give up a proton, right? So if phenol is the weakest acid, right, then it means that this acid isn't as weak. Not as weak. And that the conjugate base, not as strong. Right? So all that phenol being the weakest acid is telling us is that if we have to pick between the proton being here or the proton being here, that it's going to be more likely to be on the phenol because that's the weaker acid. Strong let's say strong acid, less likely to hold on to H. Maybe we'll put that H in red so we know what we're talking about. Weak, more likely to hold on to H. Okay. So if the weakest acid is phenol, which means it's the most likely to hold on to this proton, then the side of the reaction where it has the proton has to be the favorable side, right? So if that can help us really draw these, right? The right-hand side is more favorable. Okay, so I kind of worked backwards as to why K must be large and positive, right? Because K is saying right-hand side. If the right-hand side is more favorable, K is large, right? So what you're supposed to reason is that since K is large, the right-hand side is more favorable. And if the right-hand side is more favorable, whichever acid is on the right-hand side of the equation must be the weakest. Does that make sense? K large implies the right-hand side of the equilibrium is favored, which further implies whichever acid has the proton on the right-hand side is weaker, which in this case was, this is, C, they write it so weird, but whatever. That's the formula there. Typically, this would be written C6H5OH, but whatever. There you are. This is the reasoning. K is large, which means the right-hand side of the equilibrium is favored, which means whichever acid has the proton on the right-hand side must be the weaker acid.